Welcome. In this video, I'll be discussing solar cells. The principle behind solar cells is we're going to use light, and that light is going to interact with our solar cell in the similar kind of fashion that wind particles would act with a cell that we might use to in proportion of a ship, or at least we still do that for recreational purposes, but the way in eras in the past, ships were driven by wind, and we're going to try to attempt to move spacecrafts through space using light. Now, the benefits of this for extended missions into deeper regions of space, whatever you bring into low Earth orbit to get past that is expensive. It requires a lot of fuel to get any mass up into low Earth orbit. And then once there, whatever's left over is what you're going to be using. So if you then need to use a whole heap more fuel or other resources as a propulsion form, then that needs to be carried into low Earth orbit, and then you need to accelerate that to get to wherever you want to go. So if you want to go into like the outer solar system, then that requires a lot of fuel. The idea of solar cell is you can actually achieve acceleration using light. So thereby, you can actually use a propulsion source that you don't have to carry a lot of fuel for, or oxidizer. So in the theory, a solar cell type probe could actually achieve higher speeds over a longer period of time than rocket propulsion, at least by our current technology. So although it would take a long time to accelerate, these solar cells can continuously gain will continuously have continual acceleration, whereas a rocket has a small amount of acceleration, in large initial acceleration for a small amount of time, I should say. So, okay, so let's have a look at why they want to be using reflecting cells over absorption. So if you consider absorption, okay, so let's take absorption. Right, so if I was to, maybe I'll just draw myself a little space over here. Okay, so the idea of absorption, if I had something black, say, and I have a photon come in, and then I have no photon come out. So that's my photon coming in, and I'm just going to switch over. I'm going to say, okay, I have here, and I have my PI, and I'll have PF equals 0. Okay, because one, that's my initial momentum of my photon, and then PF equals 0, and that's absorbed. Oopsies. Okay, so, and of course these are momentum vectors, so we need to consider that. So the change of direction is important. Okay, let's draw it all. There we go. Okay, so the change of momentum of the photon is me. Okay, it's not liking that. I'll just type it out. So change of momentum of the photon would equal there we go. Okay, change of momentum of the photon would equal minus Okay, I'm in trouble with this. There we go, minus pi. Okay. All right. So pi, yeah, it's called the same thing. I'm in trouble with this. There is a bit of a. All right. Then the change of momentum cell. Okay, let's type that out. Change of momentum of the cell would be the negative of that. It's pretty easy to do with the mouse, actually. Yeah, so you got that idea. All right. So what if we had, we'll go with something different here. Okay, let's go over the reflection. So actually, let's do something a bit silvery. That's the idea. Okay, so now we've got something grayish. Okay. Now in this case, see if we can draw it now. The device is not going too well today. So we have a photon come in, and it's going to come out, and we're going to do it so it's like normal. So it's going to come out the same way it kind of came in. So it bounces at 90, bounces. It goes in, goes out. So that's just going to keep something simple. Let's keep this. Okay. So we have P initial. We'll say that equals P. P final equals minus P. All right. So the idea then, in the case of reflection, let's see what actually happens to the photon. All right, so remember, change of momentum, we've actually got two parts here, final and initial in this case. So change of momentum of the photon. Okay, let's type that out. Okay, change of momentum of the photon is final take initial, which is actually, pencil out again, equals final, which is minus P, minus positive P. Or to simplify that, minus 2P. Okay, so you're actually getting, so the change of momentum is actually twice what it was before. All right, so then what does that do to the cell? So, and this explains why we choose a reflecting surface over absorbing surface. So the change of momentum of the cell by law of conservation, so we're using this rocket form of it. The law of conservation, okay, so what if the change in body A, the change must also be body B. Okay. Okay, this is on the cell. Doesn't like me writing out what looks like letters. Can't write too small. I have to blow things up. I'm going to do it that way. All right, change of momentum of the cell. Oops. Let's do it this way. Okay. Well, change of momentum of the cell basically is going to be equal to positive 2p. It's minus negative 2p, so 2 momentum. Okay, so now we can compare that the change in momentum of the cell for the one photon hitting the absorbing cell, it just gains its momentum. If you have a reflecting surface and the photons knock onto that and then get reflected, then you end up with actually twice the momentum of the original photon that was coming onto the cell. So that's the principle behind how solar cells work. Now, the practical application, there are some proposed missions that will be carrying this out. There has actually been some testing already on some of these designs, and it's actually an interesting take on how to do kind of future unmanned missions. Now, there's not going to be a particularly good way to move people. So there's not really a frontier necessarily in that sort of technology because of just how long it will take such a device to actually accelerate. But in that sense, once you do pick up the speed, you can actually travel quite fast. But it may have its purposes in future missions, particularly into deep parts of the outer solar system. Okay, thank you for listening.